Hi, this is the third lecture on basic linear algebra. If you remember, in the first video and first lecture, I introduced you the notion of a matrix in linear algebra. And in the second video, second lecture, I solved some problems related to the lecture number 1. Today, lecture number 3, I'm going to continue the theory part of the basic linear algebra. I will introduce you the notion of equality between two matrices. I also teach you how to add two matrices, subtract them, and finally I will teach you how to multiply a number by a matrix. This kind of multiplication is called the scalar multiplication in theory of matrices. Okay? And then below this video, as usual, you find a link to a set of problems that you can solve in principle using the material covered in this video. And then again, next video would be the solutions of those problems. Okay, so without further ado, let me start the lesson today. The first thing I want to start with is the definition of equality between two matrices. So you remember the matrices were two blocks of numbers, so it might be the most natural way to define the equality between them to be the same blocks, mainly having the same dimensions, and each entry of one block is equal to the corresponding entry of the second block. And that's exactly the definition that mathematicians have chosen for the definition of the equality between two matrices. But let me write them here formally for you. So, definition matrices A, Aij, say m by n, and B, Bij, say P by Q, are said to be equal if and only if. So this is not a misprint in math literature. It means if and only if. Number 1, M is equal to P. The number of rows in the first matrix is equal to the number of rows on the second matrix. And then number 2, N is equal to Q. The number of columns from the first matrix is equal to the number of columns on the second matrix. And finally, Aij is equal to Bij for all I and j. Okay, so this is the formal definition of equality between two matrices. So we write A equal B to denote that the matrix A is equal to matrix B. Okay, so let me give you an example. Evaluate x squared plus, say, 3y if the matrices A equals to, say, 4. Let me write it here for you. So x squared, 3x plus 3, and 3x plus y, and minus 1, and b equals to 4, 2x plus 1, 2x plus 2y, and minus 1 are equal. Okay, so I'm supposed to evaluate this expression if I know that these two matrices are equal. Okay, so you know that this is possible for these two matrices because the first matrix is 2 by 2, the second matrix is also 2 by 2, so we already know that the first and the second conditions are met, so we only need to take care of the last condition. Yes, so it means that the components should be correspondingly equal together, okay, to each other. So I would say that A is equal to B. This will imply that I have x squared, the first entry here should match with this corresponding entry here. X squared should be 4, x plus 3 should be 2x plus 1, 3x plus y should be 2x plus 2y, and finally minus 1 should be equal to the last one here, which is also minus 1. So it means that I need to make sure that all these conditions are simultaneously met. The last condition is always true, so we need to be worried about the first three conditions only. Okay, solving this is super simple. So x squared is 4, so I get x equal to minus 2, or x is equal to positive 2. So as far as the first condition is concerned, x can be either minus 2 or 2, but let us consider the second condition that should also be simultaneously met. I move 2x to the left, it becomes minus x, and I move 3 to the right, it becomes minus 2. So then it implies that x is equal to 2. So it means that this minus 2 only takes care of the first one, but not the second one, so that's not acceptable. So far we know that x is equal to 2 will satisfy this condition and that condition simultaneously, so x is equal to 2. And I take this 2 and plug it in this equation and find y, yes? So then this means that instead of x I put 2, so it becomes 6 plus y, and on the right hand side I will have 4 plus 2y. And if you solve this equation, again you find y equals to 2. Yes? And then question mark that we are looking for is x squared plus 3y. So then it becomes x squared, which is 2 to power 2, plus 3 times 2, which becomes 10. Yes? So the answer to the question mark for this problem is 10. Okay. Now I want to define another thing, another concept that's called additive inverse. Yes. So for example, in the set of numbers, if I ask you what is the additive inverse of, say, number 2, for example, you would say minus 2. We want to extend this idea to a block of numbers called matrices. Yes. And the idea is more or less the same. If I want to have the additive inverse of a matrix, what I need to do is just write the opposite of the entries of the matrix correspondingly into a new block. That new block is called the additive inverse of the original matrix. Okay, so if I want to write the formal definition, so let me write it here for you. So definition the additive inverse of a matrix, say A equals to Aij m by n, is denoted by negative A, and it is defined to be an n by n to be an m by n matrix whose ijth entry is negative Aij. Yes, yeah, for all I and j, of course. So what we say is that if someone asks me what is the ijth entry of the additive inverse, then I would answer this is equal to minus aij, where a sub ij is the ijth entry of the original matrix. In another language, you can write this negative sign, and instead of this, you can write the ijth entry of this matrix. So both of them are correct. So usually when we want to prove some theorems, it's better to use this notation, that this one is equal to minus of the ijth entry of the matrix A. So for example, a simple example, if my matrix is something like this, minus 1, 0, 2, minus square root of 3, minus square root of 2, minus 3 over 2, and positive 4, then if I ask you what is the additive inverse to this matrix, you would say 1, 0, minus 2, square root of 2, 3 over 2, and finally negative 4. Very simple. Yes? Okay, now I want to define how to add two matrices together. Okay, so let me write the formal definition here for you first. So definition. Let A be equals to aij and B equals bi sub ij are m by n matrices. So both of them have the same order. Okay, so the sum A plus B is defined to be an m by n matrix such that, okay, so if you ask me what is the ijth entry of the matrix, so you see I am defining a matrix for you, so my duty is to tell you the dimension of this matrix, yes, and another duty is that to tell you what is the entries of that matrix. So by definition, if you start with two matrices of the same dimension m by n, based on the definition, this sum is defined to be another matrix of the same order m by n. And now I need to introduce you the entries. And now I say that if you are interested in the ijth entry of this sum, what you need to do is very simple. Just go and find the ijth entry of matrix A, find the ijth entry of matrix B, and then add them. Okay, so one thing that I want to mention exactly here is that I am just somehow I'm abusing the symbol addition here. So here, what you see here, I am using the same symbol for this addition on the right hand side and this addition on the left hand side. But technically they are quite different. Yes, here I am adding two matrices. I am adding two blocks of numbers together. Yes, and then here I am adding just two entries. So these are numbers. So this means that the definition of the addition of two matrices is somehow related to the definition of addition to numbers. So I might say that if you think that a matrix is just a generalization, a modification of a single number to a block of numbers, the addition of matrices is also the modification of just addition between numbers to two blocks of numbers. Yes, so be careful that even though I am using the same symbol here and there, but they are quite different. Yes, this is adding two numbers, so this is I call the ordinary addition, but this is the new addition that I am just now defining how to do it. Yes, so this is a very important fact to understand. Okay, so let me just remind you again, so to give it as a remark that if they are not of the same dimensions, this addition is not defined at all. Yes, so let me just write this here for you. the addition of matrices of different orders is not defined. Okay, so for example, if I want to add this column matrix 1, 0, 2 to this column matrix -1, 2, 0, this is defined because this matrix on the left-hand side of addition is a 3 by 1 matrix. The right matrix is also the same. So in principle, this is doable. It's defined. And if I want to do this, actually, I need to add the corresponding entries together. So it means that I add 1 to -1, the answer becomes 0. 0 to 2, it becomes 2. 2 to 0, the answer becomes 2. But say, for example, if I want to add this matrix 1, 2, 3, and 4 to this matrix 1, 2, 0, 5, -1, 5, this is not defined because this matrix is a 2 by 2 matrix, that matrix is a 2 by 3 matrix, so this is not defined. Okay. So if I want to give you another example, so let me go to Blackboard now. I can, for example, ask you to add these two matrices together from the matrices having complex numbers. Okay, but the idea is again the same. So for example, say that I want to add these two matrices together. So let me write e to power I pi over 3. And then the next one, for example, 1 minus I, 1 plus I. And then here I will have e to power minus I pi over 3. Okay, so let me add this matrix to this matrix, e to power minus I pi over 3, 1 plus I, and then I have 1 minus I here, and minus e to power positive I pi over 3. So say that I want to add these two matrices. This is doable because both of them are 2 by 2 matrices. So the only thing that I need to do is to add the corresponding entries together into a new 2 by 2 block or a 2 by 2 matrix. Okay, so this one should be added to this. So this becomes e to power I pi over 3. This should be added to this. So it becomes 1 minus I plus 1 plus I. Then this should be added to this. So I will have 1 plus I, 1 minus I. And then finally, I need to add these two. So this becomes e to power minus I pi over 3. And then I have minus e to power I pi over 3. So of course, in mathematics, we always simplify if possible. So here you can immediately see that I can simplify these two. This I and that I are gone. This I here and that I are also gone. Oh, sorry, I have forgotten to write the other one. So I had to add this one to this one. So this is e to power minus I pi over 3. Okay, but if you remember from your complex numbers studies, we know that e to power iz plus e to power minus iz is 2 cosine z. Yes, and then if I have e to power positive iz minus e to power minus iz, the answer is 2I sine z. So if you remember, this is actually the definition of complex cosine and sine function after you define the complex exponential. Okay, so but then you see that this one is exactly, this one follows this pattern where z is equal to pi over 3. So then it means that I can use this rule. Instead of this expression, I can write 2 times cosine of pi over 3. And then 1 plus 1 here is 2. And then here again I have 2. But you see, this is more or less the same pattern here, but the minus sign with minus I and minus, they match, so they are on the same term. But here minus sign is here, so it is the negative of this one. So it becomes negative 2i sine of pi over 3. Yes, so it is negative 2i sine pi over 3. And then hopefully you remember that cosine of pi over 3 is 1/2. So if I multiply it by 2, it gives me 1. And then this is 2, this is 2, and the sine of pi over 3 is the square root of 3 divided by 2. That 2 will cancel this 2, and I will be left with just I. Yes? So for example, if I add these two matrices, I will get that matrix. Okay. And one thing that's also good to know, if it's very easy, but I just want to emphasize that you can remember it. If I have two upper triangular matrices of the same order, it's very easy to show that if I add them, the result is still an upper triangular matrix of the same order. That's also true for lower triangular matrices and diagonal matrices. If I add two diagonal matrices together of the same order, of course, then the answer would be definitely a diagonal matrix of the same order, and the same for lower triangular matrix. So I really want you to remember this, even though it's very, very simple and trivial. But let me say something here. So what we are studying here is more or less very natural. Yes, so it means that what you expect, you can see. Yes, the reason is that because the definition, for example, you see the definition of the additive inverse is somehow a modification of the additive inverse by just one single number. And the definition of addition of two matrices is also a modification of the addition of two numbers. So what you expect coming for addition of matrices you expect that they should be very natural. By natural, I mean that what you expect from numbers, you should also expect somehow for addition of matrices. Yes, that is true, but this doesn't mean that you need to take everything for granted. Remember that I have introduced a new kind of adding two objects that are not numbers, even though they are consisting of numbers. So don't take these things for granted if you want to be a good mathematician. So everything which is not the axioms, not the definitions, not the theorems, need a proof. Yeah? So you need to convince yourself about that. So for example, what I'm saying is that you know transitivity for numbers. What do I mean? It means that if I have A equal to B, they are real numbers, complex numbers, or whatever, but they are numbers. And you know that A is equal to B, B itself is equal to C. So it means that you can immediately conclude that, of course, A is equal to C. Because this transitivity is true for numbers, you shouldn't take this for granted that this is also the case for the matrices. Okay? You need to show that this is indeed the case, even though, yes, it is very obvious, seems very obvious that this is true. So in the world of matrices, is it true that if matrix A is equal to matrix B and matrix B is equal to matrix C, can I still conclude matrix A is equal to matrix C? Is transitivity also works in this case? Of course, you might say that yes, the answer is very trivial, but let us go through it. Yes, I agree with you, this is obvious, but it needs proof. That's my point. So you cannot say that because this is true for numbers, I can grant this for matrices. Okay? So, for example, how do you want to show such a thing is correct for the matrices as well? So you see, you want to conclude that two matrices are the same. So according to the definition, you need to show that they have the same orders. How should I convince myself about that? I go back here. You say me that matrix A is equal to matrix B. So it means that these two matrices should be of the same order because of the definition. And now you are saying me this matrix B itself is equal to matrix C. So it means that the dimensions, the order of B is exactly equal to the order of C. So the order of B, it means that the number of columns here is equal to the number of columns there. So, and then the number of rows in A is equal to the number of rows. The number of rows here is itself is equal to the number of rows here. So now I use this fact for numbers because the row number is just a number, not a matrix. I conclude that yes, the number of rows here is exactly equal to the number of rows there. But I am using this property between numbers, transitivity between numbers once, to show that they have the same number of rows. I need to use this again to show that yes, these two matrices have the same number of columns. Yes? And after that, I want to show that every entry on A is also equal to the corresponding entry of C. So I would say that let I and J be in the appropriate range. Yes. So for example, say these matrices are m by n, all of them, and then we say that let I be an integer between 1 and m, and j be an integer between 1 and n. Then, because you are saying that these matrices are equal, so the ijth entry of A is equal to the ijth entry of B, and because you are saying that these two matrices are the same, it means that ijth entry of B is equal to the ijth entry of C. Yes, but now look again, these are not matrices anymore, these are numbers. So again, I can go back and use the transitivity of numbers to show that yes, these are indeed the case, that this one is also equal to this one. Yes, so it means that to prove such a thing, I have used the transitivity of real numbers 3 times. One, to show that the number of rows match. Second, to show that the number of columns match. And finally, to show that the corresponding elements from these two matrices also match. Okay, so this I want to make sure that you really understand that these are not the same things. Even for the second one, I am using the first one 3 times. Yes, so that's my point. For example, if I want to give you another example, so in numbers, you know that if A is equal to B, if these are numbers, and I know that C is equal to D, if I want to, I can conclude that A plus C is also equal to B plus D. Yes? But now, in the world of matrices, assume that matrix A is equal to matrix B, and assume that matrix C is equal to matrix D. Of course, they have to be of the same order. They have to be of the same order. Let us assume that all of them are of the same order. Can I still conclude that A plus C is equal to B plus D? Again, I want to make sure that you understand, because this is true for numbers, there is no guarantee yet that this is also true for matrices. Even though you can do the calculations in your head immediately and conclude that this is also the case, but you are doing something in your brain very quickly. Okay, so it means that you also appreciate that these are not the same thing. Yes, so okay, so what should I do now if I want to prove such a thing? So let us consider that all these matrices of order m by n. Okay, for definiteness of the discussion. I want to show that this left-hand side, which is a matrix, is equal to the right-hand side, which is also another matrix. So to prove the equality between two matrices, I have to show that they have the same orders. Okay, so now if all of them are the same or have the same order m by n, based on the definition of addition, the order here is m by n. The order here is also m by n. So the orders are the same. But now, again, I want to show that any entry here is equal to the corresponding entry here. So I would say let I and j, let me just don't write it again. So let us assume that I is again between 1 and m, j between 1 and n to be integers. To prove this, what I need to do, I need to prove that a plus c ij is equal to b plus d ij. This is the thing that I need to show, statement that I need to prove, yes? So I would say that, okay, you are telling me that these two matrices are the same. So based on definition of equality, I can conclude that the ijth entry of A is equal to ijth entry of B at the level of numbers. Yes, these are numbers. And you are also telling me that C is equal to D. So it means that I can conclude that the ijth entry of C is equal to the ijth entry of D. Yes? And now, these are 4 numbers. And I know that this rule of adding the left-hand sides and equate it with the addition of the right-hand sides works for numbers. And because now these are numbers, I can add them exactly according to this rule. So this means that aij plus cij is equal to bij plus dij. And now, because of the definition of the addition, which is on the board, from the right-hand side to the left-hand side, I can collect these two and write it as a plus c sub ij is equal to, the same is true for the right-hand side, b plus dij. Okay, so it means that, yes, the question mark is indeed true, but it needs some, you need to convince yourself of that. Even if that is very, very short, you can convince yourself in less than a second, but it's not trivial. You shouldn't take it for granted. And you see that this property, of course, is true. The reason that this property is true relies on the fact that this is true for numbers, because I use that fact in my proof. Okay? So yes, I just want to draw your attention about this point. Then, so you need to, whenever you have a statement which is not exactly the previous statement, it needs a proof, even though it is very related to some previous statement which you already know the truth of. Okay, so now let me write a theorem here for you. The items that I will mention in this theorem, again, might seem very obvious for you, but again, don't take them for granted. They need proofs. Okay, so this tells you the main properties of the addition of two matrices. So theorem. So let A, B, and C be matrices of the same order. And let O be the zero matrix of that order. Then, number one, it doesn't matter if I add A to B or B to A. This is called commutativity. So the order of addition is irrelevant. Yes. Now, the second one tells you that if you have 3 matrices that you want to add, the way that you collect them is irrelevant. Okay, so number 2 tells you that if I have the addition of 3 matrices, it doesn't matter if I add B and C first, when I get the result, add A to the result, or I add A and B together first, when I get the result, I add it to C. They are exactly identical. So this is called associativity. Yes. So number 3, if I have any matrix and I add the 0 matrix of that order to it, it becomes the same matrix. So this is called the identity, the additive identity. Additive identity. Okay. And finally, number 4, if I add a matrix to its additive inverse, it becomes the 0 matrix of that order, the same order of the matrix, yes? So this is called additive inverse. So as you see, the items that I have written here are more or less exactly the same items where you have for the numbers. If you consider A, B, and C to be real numbers, and this the 0 number, and this addition to be the addition between numbers, we have exactly the same properties for numbers, okay? But again, don't take the items in this theorem for granted because we have them for numbers. All of them, in principle, need a proof. Okay, so let me prove one of them for you. And by the way, these items, later we will see when I am talking about vector spaces, abstract vector spaces, it's good to know that this tells you that the set of matrices together with the binary operation of the addition of two matrices forms a group, an abelian group, okay? Just for your information, I will come and talk about these when we are talking about vector spaces. Okay, so let us do one of them, prove one of them. So for definiteness of the discussion, so let me consider that all these matrices A, B, and C and this 0 matrix are all m by n matrices. Okay, and say that we want to prove the second one, the associativity. Yes. So proof 2, item 2. So I want to prove that this matrix is equal to that matrix. So I need to convince for myself that the order of the matrix sitting on the left is equal to the order of the matrix sitting on the right. But this is completely clear because all these matrices are of the same order m by n. And by definition, B plus C is also a matrix of order m by n. When I add it to another matrix of order m by n, it remains a matrix of order m by n. And then you can say the same thing for the matrix on the right-hand side. So from order points of view, they are equal, but that should be part of the written proof, okay? But I just want to save some time, so I just told that part orally. Okay, now let me write the next part. The next part is I need to show that any element on the left-hand side is equal to the corresponding element of the right-hand side. I would say let I be a number between 1 and m is the number of rows of these matrices, and j be a number, an integer between 1 and n actually. So let me emphasize that I and j belongs to the set of natural numbers. Okay, we prove that. What do we prove? We prove that the ijth entry of the matrix sitting on the left-hand side, meaning this, is equal to the ijth entry of the matrix sitting on the right-hand side, meaning this. Okay, but how should I prove this? It's very simple, but I think it's instructive to see. So I will start from the left-hand side. Then what should I do? According to the definition of addition of two matrices, consider this matrix as one matrix in your head, and then you are interested in the ijth entry of the matrix A added to this matrix as a whole, yes? So then you can write the ijth entry of the first one by definition of addition. So this becomes AI j plus the ijth entry of the second matrix. I don't need any pair of brackets anymore here, so I just write it like this. But now look, this is a number. You are supposed to add this number to this number. So first of all, you need to know about this number. So what that number is, it's easy. If I ask you what that number is, you would say that this number itself is this number. Bij, by definition of addition, yes, Cij. Now I am going to add this number to this number, which is equal to this. So it means first I need to know this number. When the calculation is finished, I add this number to the sum. Okay, so this means this. Okay, and now these are no longer matrices, they are numbers, and you know that the addition of numbers enjoy the associativity property. So this means that I am now allowed to remove these pair of brackets and put them around the first pair. Yes, so I can write this and then put Cij outside of the pair of brackets. Okay, but now I can collect these two back based on the definition of addition of two matrices. Yes, so then it becomes equal to I plus b ijth entry, and then I have plus C sub ij. But now again, I want to collect these two back. If I ask you what is this, you say that this is the result if I want to find the ijth entry of the sum of two matrices. Which matrices? A plus B on the one hand and C on the other hand. A plus B on the one hand as a whole and C on the other hand. So this becomes the ijth entry of this matrix. And that is exactly what is sitting on the right hand side. So that's the proof. The reason that I call this proof instructive, because you can see that, of course, the associativity of the addition of matrices relies exactly on the same property for numbers, addition of numbers. So you see, I use the associativity of the addition for numbers to be able to prove the associativity of the addition for matrices. Okay? So I hope that you understand that this is not kind of a circular argument. Yes, I reduced the question of either addition of matrices is associative or not to the fact that the addition of numbers is associative or not. And because I know that the addition of numbers is associative, so I was able to prove that the addition of matrices is also associative. Okay. Let me talk a little bit about what does it mean if an operation is commutative or if an operation is associative. Yes. So if I have an operation which is commutative, it means that when I am doing that operation between two items of the corresponding set that I am considering, I don't need to be worried about the order that these items appear in that operation. It doesn't matter if I add A to B or B to A. And then, roughly speaking, this tells you that if you want to add if you want to do the operation between three of those objects from that set, you don't need to be worried about which operation should be done first, okay, and which one the less. For example, let me give you a non-example, yes? So let us go back to the world of numbers. So the division of numbers is not associative. For example, if I ask you, calculate this number for me, so 2 divided by 3 divided by 4, you should stop answering me, yes? Because it is ambiguous. It matters which one of these operations I should do first, even though both of them are divisions, but the collection of terms becomes important, yes? So because you might say that if I do this operation of division first and do the second one later, then the answer becomes 2/3 divided by 4, which becomes 1/6. But if I write it in this form, if I interpret this as this expression, Then I have to divide 3 by 4 first. If I give the priority to the second division, then it becomes 3 over 4, and the answer becomes 8 over 3. And you see that they are not equal. So roughly speaking, it means that when an operation is not associative, I cannot be lazy and remove brackets because they are necessary. But if an operation is associative, I can be lazy, yes? For example, if I ask you to calculate 2 plus 3 plus 4, it is not ambiguous at all. It doesn't matter how you interpret that. You interpret it as 2 plus 3 first and then to the 4, the answer becomes 5 plus 4, which is 9. If you interpret it as 2 plus 3 plus 4, the answer becomes 2 plus 7, but the answer is again 9. And they match. Okay? So, if I want to tell you something, we can say that if an operation is associative, you really don't need to care about the brackets, putting brackets around those items. It doesn't matter in which way you do it. But if an operation is not associative, then you need to pay more attention to be precise in your writings. Okay. And for the commutativity, it means that I don't need to be worried about the order that these things appear. Okay. So let me write one example here for you. So for example, assume that we have matrices of the same order. Let me say A plus B, and then I have plus C plus D. Is this equal to this combination A plus B plus C plus D? Yes. Of course, I don't want you to spend time on it. Definitely, you realize that they are the same thing. Yes, but I want to make sure that you understand you need to do two associativity to be able to go from the left-hand side to the right-hand side. So you need to use associativity 2 times. I want you to understand these kinds of calculations. So let me just do it for you here. For example, I start from the left-hand side. My goal is to make A alone and write B and C next to each other. So what I'm saying is that you cannot, if you want to show that this is correct using the associativity, you need to respect the way that you write. Of course, at the end, it means that I can simply remove these pair of brackets and put them around B and C. Yes, that's right. But you need to respect the way that associativity appears. Yes. So this means that if I have 3 matrices added together, it doesn't matter if I have the pair of brackets around the last 2 or I have the pair of brackets around the first 2. This is the associativity, okay? So I need to use this to be able to go from the left-hand side to the right-hand side, okay? So now, if I want to do that, I would say to myself that I can consider this as one matrix, only one matrix. Then I have the addition of 3 matrices, A, B, and C plus D as a whole. Then I can remove these pair of brackets and put them around these. Yes. So then it means that, so let me take A for this. Yeah, so I'm talking about associativity. So I take the pair of brackets from here and put them around these 2. So this becomes A is left alone now, and then I have a bigger pair of brackets that I want to put between these 2, to enclose these 2. So it becomes B plus C plus D. Okay, but now look, here is another associativity. There are 3 matrices again. Yes, I take these pair of brackets and put them around the first 2. So then it becomes A plus B plus C, and then D is left alone. And that's exactly what is sitting on the right-hand side. So that is the way that I want you to understand the meaning of associativity. Okay, and one thing is also important when you are using associativity, the way that you read the left-hand side and the right-hand side remains the same. If it is only involved with associativity. If it is commutativity, then it might happen that you have this changing of orders. So here, if I start reading from left to right on the left-hand side, it reads A, B, C. And when I read it on the right-hand side, it becomes again A, B, C. Exactly the same. Okay, now let me give you another example that somehow involves both with commutativity and associativity. Okay, so let me just open a little bit of space here. Okay, so for example, let me write this one. If I have A plus D, and then I have B plus C equals to this expression, A plus C plus B, and then plus D. So assume that you want, of course, you immediately realize that this is true because you know that the addition is associative as well as commutative. So this is completely clear, but I want to tell you that if you really want to prove it using the commutativity and associativity, how you should do it. For example, I start from the left-hand side. I see my goal is to have A and C next to each other. What I'm saying is that you cannot just move this here. Of course you can move it because it's commutative, but that is not the proof, because if you want to prove, you are only allowed to interchange the matrices next to each other. Yes, but this gives rise to this fact that I also can interchange these two. But my point is just to show this to you, okay? So don't jump ahead and just do this, even though you can, okay? So what I need to do, I see that I want to have C with A next to each other. So for example, what I can do one way, let me use the letter A for associativity and letter C for commutativity. Okay, so here what I do is I interchange these two first. It is possible, so I use commutativity, and then I would write A plus D, and then I would write C plus B. Yes. Now I use associativity, because now I consider this as one matrix, this as two matrices. Then I have three matrices, A, D, and C plus B, so I remove this pair of brackets and put them around these two. Yes, so this becomes A plus D plus C, and then B is left alone. Yes. Okay, so that's one way. And then what I do, again, I use associativity because here I have three matrices added together. I am allowed to remove these pair of brackets and put them around these two. So then becomes A plus D plus C, and then I have B at the end. Okay. And then what I do, I interchange these two using commutativity. Yes. So commutativity, it becomes A plus C plus D, and then I have B. Then here I have the addition of three matrices, so I can use associativity, and I remove the pair of brackets from here and put them around here. So it becomes A plus C, and then I have D plus B. Here I also use associativity. Okay? But now what I can do, again, I want to use associativity. How? I consider this as one matrix, second matrix, the third matrix, added together. So I remove this pair of brackets and put them around this. So again, I am using associativity. Yes? And then what I can do, I can use commutativity and to interchange these two. So commutativity, I have A plus C, B plus D. And now I use associativity once more, and I am done. Because I can see that this one matrix, second matrix, and I consider this as the third matrix, so I remove this pair of brackets and put them around these two. So again, I use associativity. So it becomes A plus C plus B plus D. And that is exactly the right-hand side. Yes? So I'm just telling you that if you really want to go from the left-hand side of this expression to the right-hand side of this expression, and you want to follow exactly the rules that you need, this is one valid way of doing that. I haven't thought about that this is the optimal way of doing, but this is exactly one way of doing that. Yes, so it means that I have to use, how many times you see commutativity? 1, 2, 3 times, and 1, 2, 3, 4, 5 times. Okay, I'm not saying that probably you might be able to do it better, but at least the all of these equalities are valid because of those properties. Okay. Okay, so that is one thing that I want you to know about. But of course, from now on, you really, if you need to go from the left-hand side to the right-hand side, you understand. It means that I can interchange any of those pairs if I want to, and I can change the collection in a way that I desire. It doesn't matter the proof. You don't need to prove it, but you need to understand what is behind that. Okay, now let me uh, uh, express another theorem. So theorem, there is a name for it. Usually it is called Additive Cancellation Law. Okay, so let A, B, and C be matrices of the same order such that we know this. We know that A plus B is equal to A plus C. Then we conclude, if we want to, that B is equal to C. Okay? Again, this is valid for numbers. Yes, this is completely clear that if I have a number A plus B, another number B is equal to A plus C, I can immediately conclude that, okay, I can cancel A from both sides and I get B is equal to C. This is also true for matrices, but it needs a proof. And the proof is relying exactly on this statement for numbers. Yes? So how should we prove that? My goal is to prove that B is equal to C. So I need to show that they are of the same order, but there is nothing to do because it is one of the assumptions of in the theorem itself that these are of the same order. So what I need to do is to show that any element of B is equal to the corresponding element of C. So for definiteness, let me just take these matrices to be m by n matrices, yes? So I'm assuming that all of these matrices are m by n matrices. Okay, so what I need to prove for the proof is this. So I would say let I between 1 and m and j between 1 and n be integers. Yes? Then I want to show that b, so then we know that a plus bij is equal to a plus c sub ij. Yes? Why is that? Because you told me that a plus b is equal to a plus c, so it means that I can conclude this statement. But according to the definition of this, so therefore, a definition of addition, I can write what? I can write a sub ij plus b sub ij is equal to a sub ij plus c sub ij. Yes? But now, this equality is not between matrices anymore, it is between numbers. And I know that numbers enjoy additive cancellation law. So it means that I can simply simplify these two from both sides because now this is a number. Hopefully you understand this is not a circular argument. So thus, what I get is that the ijth entry of B is equal to the ijth entry of C. And that's exactly what we want to show, because we were supposed to show that any entry of B is equal to the corresponding entry of C, and I was able to show that. But you see, the proof relies on the same corresponding law for numbers. Yes? Okay. And then the next thing that I want to talk about today is the subtraction of two matrices. Okay, and the definition is very similar to the definition within numbers. Yes. So, for example, if I want to subtract 3, if I want to do this difference, I would write that this is 3 plus minus 2. And what is minus 2? Minus 2 is the additive inverse of 2. So to calculate this difference, I write the first one, I change the subtraction to addition, and instead of this number, I wrote the additive inverse of that number. That is exactly the same story for the subtraction of two matrices of the same order, of course. So let me define it formally here for you. So definition. Let A, so let me write it in this form. Let A and B be matrices of the same order. Yes? Then the difference A minus B is defined as follows. It's defined by this expression. So A minus B is defined to be A plus the additive inverse of B. Okay? So for example, if I want to subtract these two matrices, so 1, 2, 3, minus 4, minus 1, minus 3, 5, and 6, what I need to do, if I want to do this difference, I need to write it in this form. The first one I need to copy and paste, and I change this subtraction to addition, and then I need to write the additive inverse of the second matrix. The additive inverse of the second matrix is just 1, 3, minus 5, and minus 6, and then I add them. So it becomes 1 plus 1 is 2, and then this is 5, minus 2, and minus 10. Yes? This is if I want to follow exactly the definition. But of course, you can convince yourself that I can just do it entry by entry. 1 minus minus 1 is 2. 2 minus minus 3 is 5. 3 minus 5 is minus 2. Minus 4 minus 6 is minus 10. So that's also doable. And then, for example, if I ask you what is A minus A, if A is in a matrix and I want to subtract it from that, this means that this is A plus the additive inverse, but this is one of the properties of the addition, that if I add any matrix to its additive inverse, it becomes the zero matrix of the same order. So any matrix minus the same matrix is the zero matrix. Okay. So I want to also express another theorem here. Again, this is also very simple and looks obvious. So let me write this here. Let A and B be matrices of the same order. Then let us write it in this form. Capital X equals to B minus A is the unique solution to the matrix equation X plus A is equal to B. Okay, so again, this seems very simple, but that should be called a theorem. So this tells you that if you have this matrix equation, assuming that A and B are given matrices, matrices, and then you want to find the unknown matrix X so that if you add it to A, it gives you B. This theorem tells you that this is the only, not only this is the solution, but this is the only solution. So this is the only matrix that you can find that will satisfy that matrix equation. Yes? Okay, to prove this, first though, I need to prove two things actually. First, I need to show that this proposed solution or this proposed matrix for X satisfies this equation. So it means that this is indeed a solution. Then I need to show that there is no more than this solution. This is the only one. Okay, so let us do the first one. If I want to show that this is indeed a solution, what I need to do? I need to replace X with this proposed matrix, and to show that this equality becomes a true equality. Yes, so what I do, I will start from the left hand side. And then I replace this X with B minus A. But because there is another operation involved, so I need to use a pair of brackets, and then I have A. But then I use the definition of subtraction here, which is still on the board. So instead of B minus A, I can write B plus negative A. Yes, that's the definition. And then I have A. Then you have three matrices are added together. So it means that I can use associativity and to remove these pair of brackets and put them around the second pair. So this becomes B plus minus A plus A. But then I know that this is the additive inverse property, so it becomes the zero matrix. And then any matrix added to the zero matrix based on additive identity, it becomes the matrix itself, and that is exactly the right-hand side. Yes? So the definition of subtraction, associativity, additive inverse property, additive identity property are all involved in this very simple proof. Okay? And now I want to show that this is the only solution. So assume that this is not the case. Assume that this is not the case. Assume that this is not the case. And x1 and x2 are two distinct solutions to this equation. Okay, so what does it mean? When you say x1 is a solution, this implies that I can replace x with x1 and the equality is valid. So this means that x1 plus a is equal to b. For the same reason, when you say that x2 is a solution, this means that the same thing for x2. But now I have two matrices, x1 plus a, x2 plus a, are equal to the same matrix B. So it means that they are equal themselves, yes? So this becomes x1 plus a is equal to x2 plus a. But now look, we have just this additive cancellation law, yes? If I have a plus b, a plus c, a is in common, so I can eliminate that. So then you see here the same story happens, but I have a on the right hand side, but because of commutativity, I can just write it in that form. Anyway, this a can be cancelled, and then I get x1 is equal to x2, and that's a contradiction. Because I have assumed on the one hand that x1 and x2 are two distinct solutions, they are not the same, and then the consequence of this assumption gives me this, that they have to be the same. So it means that they are distinct on the one hand, they are the same on the other hand simultaneously, and that's a contradiction. So it means that we cannot have more than one solution for this simple equation. So what is, in principle, later, if I want to solve this equation, I can just solve it as if I am just solving a numerical equation. But if you remember, if I have x as a number, And if I have a number a added equal to b, if I want to find x, of course, I can move a to the right and just change the sign from positive to negative. I can do the same thing for matrices, yes, addition of matrices. Okay, so that is also one thing that I want to talk about. Now, let me open a little bit of space here. Okay. So now we want to talk about the last part of this video, and it is how we multiply a number by a matrix, the definition of the scalar multiplication. Okay, so let me just define it here for you. So I would say let Aij be an m by n matrix and let, say, lambda, for example, be a number. The product of A by lambda is denoted by lambda A, and it is defined to be an m by n matrix such that the ijth entry of this new matrix is defined to be lambda times of the entry on the ith row and jth column of matrix A. So simply speaking is that if you want to multiply a number to a matrix, what you need to do, take that number and multiply it on each entry. Yes? And then you get this new matrix. This multiplication of a number by a matrix is called scalar multiplication. So for example, if I have A is equal to this matrix, square root of 2, 2 square root of 2, 0, minus 1, 2, and minus 3, then if I want to multiply square root of 2 by A, let us say minus the square root of 2 by A, I need to take minus the square root of 2 and multiply it by all these entries. And then the matrix that I get is of the same order, and it's called the matrix, the scalar multiplication of minus the square root of 2 by A. So the answer becomes minus the square root of 2 times the square root of 2 is minus 2. This one multiplied by that is minus 4, 0, and then you have positive square root of 2, negative 2 square root of 2, and then finally positive 3 square root of 2. So multiplying a number by a matrix is very simple. So let me give you a little bit better example here. So let A be this 2 by 2 matrix, 2, 0, 0, 3. B be this matrix, 3, 0, 0, 2. And C be this matrix, 0, 3, 0, 0. Determine the numbers alpha, beta, and gamma such that
So alpha times A plus beta times B plus gamma times C is 3 times I. Okay, so here what does it mean, I? If you remember, I told you that letter I is reserved for the identity matrix in the theory of matrices. But of course, we have infinitely many identity matrices of different order, but it is completely clear from this context that this should be a 2 by 2, yes? Because here I have 2 by 2 matrices, and when I multiply them by some numbers, the order is not changed, and when I add them, the order is still 2 by 2. So if this makes sense, this only makes sense if this identity matrix is a 2 by 2 identity matrix. And the rest of it is very simple. You just replace A, B, and C with these matrices, do these operations, and then you calculate this alpha, beta, and gamma. Okay, so how should I do that? So I will start replacing A, B, and C with these given matrices. So I will have alpha, matrix A is 2, 0, 0, 3, plus beta is another number multiplied by the second matrix, 3, 0, 0, 2. And then you have gamma multiplied by the third matrix. This is supposed to be equal to 3 times the identity matrix 2 by 2. So it is 0, 1, 0, 0, 1. This is the identity matrix. It's a diagonal matrix on which the entries on the main diagonal are all equal to 1. Yes? So, and then I calculate this. Let us do it step by step. So according to the definition just right now, is a number, this is a matrix, so I multiply this number inside by multiplying this alpha on by all these entries. So then it becomes 2 alpha, 0, 0, 3 alpha. The next one, the same, becomes 3 beta, 0, 0, 2 beta. The next one becomes 0, 3 gamma, 0, and 0. And the right-hand side is still 3 times, so I can multiply 3 inside also. So it becomes 3, 0, 0, 3. And then you know that this is not ambiguous because addition is associative, so I just add them simply. So the first entry, the first entry, the first entry, they have to be added. So it becomes 2 alpha plus 3 beta. 0, 0, and 3 gamma. So it becomes 3 gamma. 0, 0, 0. It becomes 0. 3 alpha, 2 beta, and finally 0. This is the sum on the left-hand side. Then it should be equal to the matrix on the right-hand side. Yes? And then you can compare that. Yes? All these entries should be equal to the entries on this side correspondingly. So this means that 2 alpha plus 3 beta is supposed to be equal to 3. 3 gamma should be equal to 0. And 0 is equal to 0. So if you want, you can write it, but it doesn't matter. And then I have 3 alpha plus 2 beta is equal to 3 again. Of course, I am looking for alpha, beta, and gamma, so gamma is clearly 0 from this equation. And then I need to solve this system of equations for alpha and beta and find them, yes? And I think it's very simple. So you see, if both of them are equal, so this means that 2 alpha plus 3 beta is equal to 3 alpha plus 2 beta. So if I move 2 alpha here, it becomes alpha. If I move 2 beta here, it becomes beta. So alpha and beta are actually the same. And then, for example, for this equation, I can write 2 alpha instead of 3 beta. I again write 3 alpha because they are equal. And on the right-hand side, I have 3. So alpha is 3 over 5. And when alpha is 3 over 5, beta is also 3 over 5. So the numbers that I was looking for, alpha and beta are both equal to 3 over 5, and gamma is equal to 0. Yes? Okay, but then I want to state another theorem, the properties of this multiplication. So theorem, the properties of scalar multiplication. So I would say that let alpha and beta be numbers, and let A and B be matrices of the same order. Then So there are some properties that I want to list them here for the scalar multiplication. So number one, if I multiply 1 by any matrix, it gives me the same matrix. Again, these are very, very obvious, but these are not trivial. They need proof. So number two, if I multiply minus 1 by a matrix, it gives me the additive inverse of that matrix. Okay? So number three, if I multiply number 0 by any matrix, it gives me the zero matrix. Because this differentiating between these two is a little bit hard with handwriting. So let me just write m by n here and then m by n here. Yes. So it means that if I multiply the number 0 by the m by n by any m by n matrix, it gives me the 0 m by n matrix. Number four, it doesn't matter what is my number. If I multiply it by the zero matrix, so let us call it 0 m by n, it gives me the same zero matrix back. So somehow these two are similar to this fact that the product of two numbers is equal to 0 if A is 0 or B is 0. But that's not exactly the same thing, because in the numbers, both of them are coming from the set of numbers. But here, one of them is a scalar, we will talk about that, and is a number. The other one is a matrix, okay? So these are trivial, but there are some other ones. So let me write the other one. So number 5, if I have a matrix, if I multiply this matrix by a number beta to get a new matrix, and then I multiply this by another a number alpha, it becomes exactly the same. If I multiply the numbers first and get a new number, and then multiply that new number by the matrix A. Yeah. So if I want to write, so in the product of numbers, we see something like this. This is called associativity of the multiplication of real numbers. But don't get confused. This is not associativity, even though it looks very similar to the associativity. And it will be proven using associativity, okay, of the numbers. But this is not associative because alpha and beta are scalars or numbers coming from the set of numbers, but A is coming from the set of matrices. So associativity, when I have associativity in any case, all these elements should come from the same set. So it is similar to associativity, but it's not associativity. So number 6, if I have a matrix A, and if I have another matrix B of the same order, if I add them and I decide to multiply this sum by a number, I can write as alpha A plus alpha B. So I would say that I am distributing alpha over A plus B, but again, this is not distributive law. This is comparable to this situation that if I have A, I want to multiply it over B plus C, I can write AB plus AC. Yes, this is called distributive law, distribution of multiplication over addition. But again, you see all of them are of the same kind. But here, A and B are matrices, but alpha is a number. But again, the proof, we will prove some of them. You see, the proof of this depends on the validity of this distributive law for numbers. And then finally, if I haven't missed anything, hopefully yes, there are 7 of them. So if I have two numbers added together, and then I am supposed to multiply this sum to the new matrix A, I can just do it like this. Yes, so these are the 7 properties that I want you to know about scalar multiplication. So again, let us prove one of them. For example, it doesn't matter which one. So what I want to make sure that you understand, this relies on associativity of numbers, the product of multiplication of associativity. Multiplication of numbers is associative. This relies on that fact. But number 6 and number 7, both of them rely on this fact that multiplication is distributive over the addition. Okay, so let us, for example, choose one of them. Let me, for example, solve this one. Okay, so Again, the left-hand side is a matrix, the right-hand side is a matrix, so I want to prove the equality of two matrices. I need to prove that they are of the same order, but this is you can easily convince yourself because A and B are of the same order, so these are of the same order. But what I need to do is to consider the ijth element of the left-hand side. So again, if I want to be very precise, I need to say that I runs from 1 to the number of rows and j runs from 1 to the number of columns. But assuming that I have done all those things, I consider the ijth element of this matrix. Based on definition, I can write alpha times ijth entry of this matrix. Yes, but now there is a definition for this, and then I can write it as the ijth entry of the first one plus ijth entry of the second one. You see why I am doing this? Because this is a number. This is also a number. I want to multiply this number by that number. So I need to know this number to be able to do that. If I ask you what this number is, you would point me this, and then I want to multiply alpha to this expression. So I have to put a pair of brackets and then write alpha here. But now these three are no matrices, they are numbers, and numbers enjoy this distributive law. The multiplication of numbers is distributive over the addition. So I can do the same thing here. So it becomes alpha aij, then I will have alpha bij. Yes? And then this alpha, based on this definition, actually goes in where the definition was here, you see? So if I have a number, I can move it inside, or if it is here, I can pull it outside. So here, I can move this inside, so it becomes alpha a ij plus alpha b ij. Yes? And then based on the definition of addition, this becomes alpha a plus alpha b ij. So it means that I started from this, and I was able to show that these two are equal. So, and then you see that this property for numbers plays the vital role so that I was able to prove this. Okay, so if I want to say something about what happens if I want to add two matrices, can I add A plus A and write 2A? It seems probably a very trivial question, but it needs understanding. So let me just open some space to be able to talk about that. Okay, so what I'm asking is that if I have a matrix A and I add this matrix with itself, can I write 2A? Yes? Why is that the case? Of course I can, but why? Because in principle, what does this mean? Let me start from the right-hand side. So when you write 2A, instead of 2, you can write 1 plus 1A. Yes, 1 plus 1 is the same number as 2. Okay, and then you have this property. Do you remember? The property was this. If I have alpha plus beta times A, I can multiply alpha by A, I can multiply beta by A, and then add these new matrices. Yes? That was one of the properties in the previous theorem. So this means that I multiply 1 by A, and then I multiply 1 by A again. But there is also another property, number 1. 1 times A is A, 1 times A is A. So now if you look here and here, it means 2A is equal to A plus A. But this relies on these properties of this theorem. Otherwise, you were not able to write such a thing. But from now on, of course, you are on the safe side. If you have A plus A, I don't know, n number of times, n summands, saying that n is an integer, positive integer, then you can safely write n times A. Or, for example, can I write minus A plus B to be equal to minus A minus B? The answer is, of course, yes, but if you really want to understand what's going on is this. Minus the additive inverse of a matrix, you see this property that I wrote here. Number 1, the additive inverse of any matrix is equal to minus 1 times that matrix. So then it means that the additive inverse of A plus B is equal to minus 1 times A plus B. But then I have the last, I have this property that I proved it here actually. If I have a number, I can distribute it inside. So this number here is -1 now, so I can distribute it inside, so it becomes -1 times A plus -1 times B. But then also another property that -1 times A is the additive inverse of A, so this becomes minus A, and then plus additive inverse of B is minus B. But now, based on the definition of subtraction, this is exactly minus A minus B. So it means that, yes, if I want to write such a thing, I'm on the safe side. You can just do that, yes? Okay, so there is also a few things left, so let me complete them. So let me open a space here. So another theorem that I want to talk about, a theorem let A and B be matrices of the same size, of the same order, such that lambda times A is equal to B for some non-zero number lambda. Then, what can I conclude if I want to? Then A is 1 over lambda times B. Yes? So if I have this scalar multiplication on the left-hand side equal to a new matrix, if I want to know what A is, I can simply multiply 1 over lambda by B, but of course, for 1 over lambda to make sense, lambda has to be non-zero. Okay, but what is the proof for this? I would say lambda A is equal to B. Because you have granted that lambda is not 0, it means 1 over lambda exists. So I can multiply both sides by 1 over lambda. So this means 1 over lambda multiplied by lambda A is equal to 1 over lambda B. But then, you see this property is still on the board. If I have two numbers, like this, alpha and beta and A, I can multiply the numbers, and when I get the number, I can multiply it by my matrix. And that's exactly the same story here. So I have two numbers, 1 over lambda is a number, lambda is also a number, so I can write what? I can take the pair of brackets and put them around these two numbers. So it becomes 1 over lambda times lambda, and then I have A left alone. On the right-hand side, still I have the same expression. But this is something very clear. 1 over lambda multiplied by lambda is just 1. So this means 1 times A is equal to 1 over lambda B. But then this is also one of the properties of scalar multiplication, that 1 times A is just simply A. Yes? Okay. So let me give you one example. Solve the following matrix equation. A and B are given matrices of the same order. So let me write this equation for you here. The equation, I have chosen it from this book that we are following. X plus 1 over 2a is equal to 5x minus 3 over 4b. I want to solve this equation and find the matrix B, matrix X. Okay, now you see I have the sum of two matrices and there is a number. I want to multiply this number by this sum. According to the rules on this theorem, I can do that exactly according to this rule. I can multiply 3 inside, so it will give me 3x. But can I write 3 over 2a? Be careful, it seems a ridiculous question, but it is not. Why I can multiply this here and write it 3 over 2 is because of this. I'm multiplying 3 by 1 over 2a. But then, because of this property, I can remove these pair of brackets and put around this. It becomes 3 times 1 over 2a. But of course, 3 times 1 over 2 is 3 over 2 times a. So this is actually the reason that I multiply 3 by this and write it 3 over 2. So you need to respect that. I'm not saying that you need to write this down, but you need to understand this is because of this property. Yes. And then the same story there. So it becomes 5x minus 15 over 4b. And I told you in the previous theorem that we can move these terms around, respecting that I need to change the signs from negative to positive, from positive to negative, yes? So here I have 3x on the left, I move 5x to the right, to the left, it becomes negative, and then I will have minus 15 over 4b on the right, I move this to the right, it becomes minus 3 over 2a. And then this one, so let me open a space here. So this becomes 3x minus 5x is minus 2x. And on the right-hand side, I will have, let me write a first. It doesn't matter, of course. And then minus 15 over 4b. But now, according to this theorem, if I have lambda of a matrix times a matrix equal to another matrix, I can write a is equal to 1 over lambda that matrix. So I can write this expression x is 1 over minus 2 times this expression. But again, because of the properties of the previous theorem, I can distribute minus a half inside. So then this means that my x is equal to, if I multiply these two, it becomes 3 over 4a, and then it becomes 15 over 8b. Yes? Okay. So one point is that, of course, the division of a matrix by a number is in general not defined, and you don't see them in the context. But if you somehow if you see something like this, a matrix divided by 2, I don't want to use this notation at all, but this means somehow that 1 over 2 times a. So, but by no means, for the time being, we don't have this expression that 2 divided by a matrix. That's not defined yet. We can somehow define it, but we haven't defined it, and we won't define it probably in this course. But if you see something a divided by 2, it means this, but I really recommend you to avoid this notation. And finally, I want to finalize this session by one theorem, okay? And that is very similar to the zero product rule for numbers. So let me just motivate you here. Okay, so do you know that in numbers, a times b is equal to the zero number? If this happens if and only if either a is equal to 0 or b is equal to 0. Yes? So the same is also true for a scalar multiplication in matrices. So if I have lambda, so let me write theorem. Let lambda be a number and let A be a matrix. Okay, then lambda A is equal to the zero matrix. This is the zero matrix of the same order as A. if and only if, so you remember IFF means if and only if, lambda is equal to 0 or A is equal to the 0 matrix. Okay? So because this theorem is expressed with if and only if, it means that this is actually indeed two theorems. So first we need to assume that this is true and show that this is true, and then we need to assume that this is true. We have to prove that this is also true. Okay, so let us go from this direction. So let me write proof. Let us consider this direction, from this direction to that direction first. So lambda A is equal to 0 by assumption. I want to show that lambda is equal to 0 or A is equal to the 0 matrix. I would say that if lambda is equal to 0, then we are done. Yes? Why? Because I want to show that either this happens or that happens. If you say that this happens, okay, I am done. If not, and if lambda is not equal to 0, then I can use the previous theorem. If I have a non-zero number times a matrix equal to matrix, this matrix is 1 over lambda that matrix. This is crucial. If not, and if lambda is not equal to 0, then based on the previous theorem, lambda A is equal to 0. I can conclude that A is equal to 1 over lambda times 0, but any number multiplied by the 0 matrix is the 0 matrix, so it means that A is equal to 0. So what does it mean? It means that if lambda is 0, I am done, because I want to show that either this one happens or that one. If not, and if lambda is not 0, then I can use the previous theorem using this idea and show that the second one happens. So if this happens, either this happens or that happens. But the proof of that one is actually very simple, so let me just tell you orally. I want to go from here to there. So if this happens, if lambda is 0, instead of lambda I substitute 0, and then 0 times A is 0, the matrix 0. And if A is the matrix 0, here I replace the matrix A by the capital 0, then this becomes 0 again by the theorems that we have so far. So in principle, this is a similar idea of the zero product rule for matrices. Yes. So if a number multiplied by a matrix is 0, so a number multiplied by a matrix is equal to the 0 matrix, if and only if either the number is 0 or the matrix is the 0 matrix of that order. Okay. Okay. So I will stop here. And then below this video, you will find a link to the PDF file containing some problems that you can improve. Using them, you can improve your skills and understanding around the topics and material that I covered in this video. If you think that my videos are somehow useful for you, I would appreciate if you can give me a thumb up and support me by subscribing to my YouTube channel. Until the next video, goodbye. Thank you.